Okay, yeah, so contracts are nothing new to us. We've got them in the standard. There's still things that bite us. And the favorite example here is that if you publish this interface, people get really mad without that extra clause there because they want to pass nulls if they're in cases where they don't have anything to copy. And the problem with our contracts is that they're in documentation only, and people don't pay as much attention to writing them as they need in order to write good code. Sorry? Or reading them. Yeah, and of course, the more thorough you are writing them, the less likely anybody will read them. Now here the second example is interesting because all the required clauses are both linear, where the binary search is order n, and the binary search is log n. And so in general, you can't actually afford to check the things you can express. And you've got another. So I'm going to start with some simple definitions. So when we talk about a wide contract, this is a contract that has no preconditions. And here's some examples. And we have then to widen a contract is to allow additional calls that wouldn't have been allowed before. And of course, when we have to narrow a contract is to say that what used to work doesn't work anymore. And we try not to do that, of course. But and of course, we all know about undefined behavior. And here we have memcopy reading from uninitialized memory. But when we have a library, one of our library functions, if we say you violated a precondition, have you produced undefined behavior? Well, it depends on what's in the body of the function. Yeah.
I disagree with your definition of undefined behavior. Undefined behavior does not mean a crash. It means you have no idea what.
Well, this is a point here that you have to assume if you violate the preconditions. Oh, sorry. The point was that
it's not guaranteed to go boom, even if it is undefined behavior.
you have to assume that. Okay, the question was the remark was that undefined behavior doesn't mean it crashes. Sorry. You hope it crashes, yeah. But let's see, where am I? But the point being here that violating a precondition on a library isn't the same as undefined behavior as far as the language is concerned, because depending on what's in the body of the function, it might do something that the language doesn't define or not. And so you have to assume if you violate the preconditions that you've got undefined behavior, but the compiler can't assume that that undefined behavior has happened because it just depends. And of course, okay, so we have a familiar C-style assert, and there are problems with it is the compiler can't see it, and the compiler's not allowed to act on it unless you go and redefine assert to do something, and then but of course, this is undefined behavior too, to put that define in there. So unless your implementation says you can put that there. Okay, so why do people want contracts? It turns out there's a lot of different constituencies for contracts, and a lot of things people want out of them. One very large constituency wants to use them to check static correctness on programs, and not just on specific call sites, but be able, when we have inlines and templates, that the compiler can see through a lot of levels of the system and can track requirements up and down the system that is hard to see all at once for a person. And they have, some people want to go so far as to take post conditions on one function and feed that into checks on on the subsequent preconditions. And we call that stitching. People want runtime correctness. It's very easy to misuse libraries, and it helps if we can catch them at runtime. Call a handler, log the state, maybe phone home on the next startup. Microsoft particularly was very interested in better security. They want postconditions to run and actually verify that some buffer has been zeroed out before the function returns. There's a lot of people who have no interest in it except for better performance, feeding data into the optimizer. And the optimizers have a very difficult job to do. And many of the analyses that they, in principle, could do, they can't afford to do because it's NP. And so they want to use preconditions and assertions as oracles. Now, this final point here is might be a little subtle here, is that not checking your preconditions in your function makes them a little faster, but optimizing based on your preconditions can make them a lot faster than just not checking them. And so people who want to have functions with code with no undefined behavior at all will hopefully find it harder to argue for that when the performance makes a big difference. In connection with better runtime correctness, we find that runtime checking makes testing more effective. And we find more errors that way than regular tests. Some people want them specifically because they don't have unit tests or can't feel like they can't afford to write unit tests, and they want to use it as a substitute for them. I won't comment on that. And of course, then there's the relationship between library users and library writers, which when we have a better check on whether the library is used correctly, that improves the relationship between the parties and maybe leaves the implementer more time to actually improve the library and not chase spurious bug reports. Also, of course, if you can log violations and then the log goes into the bug report, say it's an internal violation, you get a better checking. Okay, so, but it turns out there are complications, and one of them is that you can't actually write down a whole contract in C++, no matter what we do to the language. And here's an example where the precondition is based on the entire past history of the program. And there's no way you could write anything that checks that, or that expresses the postcondition even. And even where you can, you might not be able to afford to. So here we have a standard sort, and you can't actually check that B and E are from the same container, but checking whether after you ran sort that it really is a permutation of the input has besides being an n-squared process, it's kind of hard to describe what it's comparing against what. B and E after it's run refers to an array that's supposed to already be sorted, but what is it checking it against? And that's what I said. Okay, so then we have the problem that it turns out that when you fully annotate a function interface, if you put it in the interface, you get very long declarations. And this was something Google reported, is that they had been experimenting with this and found that they really couldn't afford to have full header level annotations, and they took most of it out and just put in the simplest ones, and then they put the rest in the function body. And point here is if you're going to make it so huge, you'd like it to be complete, but you know it's not complete. And all you can put in these things typically is expressions, and sometimes you'd like to say something more about what's going on. Lisa, I added this after Lisa's comment, by the way. Okay, so then you have another complication is in C++. In C++, there's a lot of ways to get to a function, even if you call it directly. You can call it through you have a virtual base, and you end up calling a derived class member. You call through a function pointer. You have a specialization, and so you're using the base class interface and getting the specialization. And similarly for overloaded function templates. And we'll get to why this matters. In general, that if you have two ways to get to a function, you might want to have two different contracts for it. And sometimes you actually might want a wider interface in the derived case. And I'll get to examples to that if I have time, but I probably won't. Runtime complications. Of course, there's no upper limit on how expensive it could be to do a check that you actually can do. But a lot of cheap checks catch common mistakes and are really valuable for that purpose. But C assert just aborts, and we've seen that there are much better things you can do than abort. So, but then you have to say what you want done. And again, this business of we'd like to check things that we can't afford to because it violates the complexity guarantee on the function. But we'd still like to be able to run those checks under certain circumstances. So that leads us to build modes, where we build it either to checking or not checking. And that leads to questions about, well, if something's compiled into the function and that function ends up in this translation unit or that translation unit, then it sort of matters how this translation unit or that translation unit, what mode it was built with. And so you expect circumstances where where you thought it would check, but it didn't because it ran in a different translation unit. And so, of course, you get around that by compiling everything with the same mode, but sometimes that's hard, especially if you get translation units from somebody else. So these checks can be useful to the optimizer, but there are complications here because let's see, which one am I starting with? Okay, so if you have a check at runtime, the optimizer and the optimizer knows that the handler can't return, then it can assume that the assertion is correct from that point on. If checking's turned off entirely, it can assume that that's true in all the code that leads up to that assertion also, and it will, up to the back to the last I can't even think of this word now. Side effect. Now there's a subtlety here. Is that here's an assertion that uses p pointer and dereferences it, and so regardless of what happens, what else might happen, the compiler's going to look at that and assume that p is not null, and that's going to propagate forward and back, which could be amusing. An interesting thing I just found out this week, Microsoft experimented with this technique of replacing, of expanding assert to assume, and they found that a lot of code was slower. And the reason is that their optimizers, when they get too many facts, they throw up their hands and stop optimizing. And maybe when there's a lot more of these facts that optimize, or a lot more of this instrumentation, optimizers might have to do better at that somehow, and maybe even try less hard to figure out facts for themselves, because that's the expensive part. Okay, you can have a case where a check expression has an implication that would cause a subsequent check, runtime check, not to be, or to be elided entirely because the compiler knows that it's already satisfied. And that upsets some people, but the compiler people say that's unavoidable. And I don't argue with compiler people. Now, I'm going to have something later about postconditions that depend on value, pass by value arguments, which has interesting consequences. One of the proposed features of one of the features in the proposal is to mark an expression as axiom, or some other keyword, that means never run this under any circumstances. And there's an interesting consequence of that, is that an axiomatic expression can call functions that haven't been defined. And then the static checker has to use whatever it knows about that function, such as what postconditions it's been declared for it, or even what preconditions have been declared for it. And so you can package your postconditions and preconditions on unimplemented functions, maybe. We haven't really discussed that very much. And then, of course, we have build modes. And it turns out there's a lot of different combinations possible. And nobody's going to be happy with any one of them. And so we have a three-way choice for what tests are actually run at runtime. We have the issue of whether a handler is allowed to return and continue running, and it turns out to be a lot more important than many people assume. And then the issue of how to what function do you want it to call if there's a violation, and then we have instructions to the optimizer about what it can do with the statements you put in. It's been long and complicated getting the proposal ready for inclusion. So we have participants here, and there's a lot more, of course, but these are the ones who have been most assertive about their needs. And this is a kind of a timeline of how things have gone. The interesting parts of this is the last two lines. We're expecting it to go into C++ 20 or 19, but it will probably go into a TS well before that, and the compiler vendors will implement the TS well before C++ 20. And most likely any C++ 17 implementations will have this implemented, guarded with it as a TS. And you'll be able to use it directly, and it's fairly likely that their standard libraries will have started to get instrumented using these because they don't have any backward compatibility issue. Okay, so then there's details. So this is a example of what we expect it to look like. Again, we have sort here. And the first precondition there, it's verifying that the comparison function actually operates correctly over the values that are in the sequence. Post is sorted, and the third one is an example of an unimplementable function, but which could be standardized and which then compilers could act on. This reaches either terminates and returns true, or it might not never terminate, or it might crash. But it's something you'd like the optimizer to, if it can see that it doesn't reach, that it should refuse to compile it. Then we have these asserts in the body, and again, this is permutation. It's like what can you put there? You'd actually have to make a copy of the input at the top before you started, and compare against that. But then if you have compiled out the assertion and don't want it to run, how do you compile out the copy? And so there's lots of things you still can't do. And of course, this is just sample syntax, and people are still arguing over that. In particular, should it have a comma between pre and axiom like the syntax, existing syntax requires? And we like having a colon there instead of putting everything after the keyword in parentheses. And so what the upshot of that is that this syntax won't go through GCC 6 or Clang 3. What is it? 3.89 now? Yeah. And that really matters. And then there's unresolved how to mention the return value of the function, which this one luckily doesn't have. And do we want to call it pre and post, or do we want to call it requires and ensures, or that's the sort of thing committees like to argue over. So one thing we've found is that newly instrumenting any significant library breaks all the programs that depend on it. It will refuse to compile, or it'll fail the tests because you're probably misusing the library. And so we need transition support. And what that means, one thing it means is that we've got to backpatch our C++14 compilers to allow the new syntax, even if it ignores what it says in them. And I'm proposing that they have this extra option that you can list off attributes that you don't want it to that you want it to ignore, so it can still report misspelled attributes that you do want it to pay attention to. Keeping two different versions of a library, one instrumented and one not, sounds like a recipe for real pain, and or macros. And so we'd really like to be able to feed an instrumented library through a compiler that hasn't had it fully implemented yet. I think the C++ standard library counts as a significant library. And so when the vendors instrument their standard library, there'll be a lot of surprises, and you'll really appreciate any sort of transitional aids. Okay, so runtime postconditions have a little problem. That is that the static checks, it doesn't really mean anything to talk about the value argument at the end of the function. I mean, for instance, when you implement sort, it's very common to overwrite B and E in the body. But it's not really well defined what it means to say B and E at the end of the function. And you certainly don't want to be writing expressions depending on them. And so the solution that Bjarne came up with for this is to say that it's ill-formed to mutate an argument that's mentioned in a postcondition. Now, a value, a pass-by-value argument. But they're not const, because you don't want the function to, you don't want name lookups to depend on whether the postcondition is there. You want it to be the same even if you wiped out the postcondition. So it's not mutable, but it can't be const, and anyway, const doesn't mean not mutable. So what this really means is that these values are non-const, but they better not be mutated, and the compiler can't always tell whether you did. And so this will be another case of diagnostic not required. And that's perhaps unfortunate, but I don't see any better way around it. Okay, controlling when and whether you want contract annotations to be actually evaluated is also complicated. And here I imagine 3 different compiler command line flags to control this. And spelling, of course, is still up in the air, but here we see an example of contract runtime level. If you don't say, then the default ones get run. If you say none, then that's release mode. And audit level is something you do to, if you don't care about the runtime of the program and want to get more information about what's going on in it. Then the second one is specifying a handler. And this is something that would probably be on the link line. And the third one is something about, is the most important one for transitioning, is that if you have a program and you run it with an instrumented library and it hits an assertion failure, you don't want it to quit right there. You want it to continue running and log more violations and get as many logged as you can before you go in and fix it. But that has consequences on code generation and optimization, which we'll get to. And then someone pointed out that we have sanitizers in compilers now, and it makes perfect sense for the sanitizer to call. Let's see, how am I doing here? For the sanitizer to call the same handler. Then we have static declarations. The proposal that's going in is that all the different ways of getting to a function must have exactly the same pre and post conditions. And that's very restrictive, but it might be relaxed later. It's in general uncomputable to say whether one set of conditions is a subset of another. And we talked about stitching, and we talked about undefined functions being used. Optimization is complicated. Compiler needs permission to use annotations to optimize because it actually let's see, we've been over that. Yeah, okay. So it interacts with the runtime, with the runtime checking level, and again, we talked about dereferencing a pointer. Does the pointer's implied non-nullness propagate? Yes. Forward and backward? Yes. And potentially eliding other checks or your code or regular code. A consequence of that is that it matters what order your assertions appear in. And sometimes an optimizer will not elide a subsequent check, and then a later compiler will, because it got smarter. So you can experiment with this using macros. You might even reassign assert. And now your implementation is allowed to produce ODR, what would be ODR violations in your program by fiat, but you don't get that latitude, even if you use the same macro. So it all depends on what your vendor is willing to support. what we'd like to do immediately is hack Clang and GCC to support this, and this is kind of the order you would do it in if you're trying to prepare for the advent of contract support. So then we have some resources. These are links for papers that have had to do with the subject, and there are more. And that's all I got. I don't know how am I doing here. Okay, so I have time for questions. Yes.
You have to decide where to put them. Do you think that should be part of an ABI, or do you think that's just...
It could be part of an ABI. There's indefinitely complicated suggestions on how that could be done. You could have the function body have preambles and postambles that only that get entered differently depending on modes. There you can imagine circumstances where you want the check to be done in the caller because you know it's not going to be done in the callee in the library, and so maybe there's even more mode flags. Something I neglected to mention here, it was in my notes but it didn't get onto a slide, is that assertions and preconditions are code, and code must be tested. So there's another issue of like, well, how do I test that my assertions and preconditions and whatnot actually are run correctly and are catching the things I want them to? And it turns out that what you want it to do then is to put in a handler that throws. But if you put in a handler that throws and it is annotating a function that is no accept, then if the handler throws, then it will call abort. And there doesn't seem to be any way around that, but except that maybe your handler just does a long jump instead, and you leak all your objects. And that's probably okay in a test driver. Okay, sorry, there was a... Right, and Bjarne is writing that. Oh, sorry, the question was, there's going to be another proposal before the next meeting.
So it's actually like, it actually is a proposal, not just a paper.
He is, right now, what we have now is an informal proposal without working paper text, and that will probably be the state of it in Oulu. And after that, then we need to come up with good working paper text, and that will probably involve a lot of input from compiler vendors, who will probably have a lot to say about this.
Yeah. I contracts to, like one thing I'm thinking is, I could put some conditions that log entry and exits to my function, certain conditions happen. And do it in my handler so it doesn't fail like it's using the logging. And expand on that.
Yeah, so you could imagine the compiler adding its own, the question was, might I be able to use the same facility to log entry and exit on my functions? And I could imagine the compiler inserting synthetic preconditions and postconditions for that purpose, and that might be a command line, or it might be another attribute that you would put on a function. Yeah, and so we have lots and lots of ideas that for things that could be added, such as a library of useful handlers that we know, or handler functions that we know are useful, that would be in the standard library, and you just have to mention those instead of having to write them. And they could maybe like have a global pointer somewhere that says where to jump to instead of you having to put it on the command line.
Can you describe how it's going to be specified regarding, you describe compiler options? I'm
Yeah.
imagining that those aren't going to be a part of the specification, it's just
Right.
implied that something like that will exist, and it's really going to be implementation defined.
Right. There's a lot of hand waving text that's going to go into the working paper. The question was like, how can we talk about command line options in the standard? And the answer is that we're very limited in what we can say. But the compiler implementers will know what to do, and there will be very strong pressure on the compiler implementers to do it right, and maybe even compatibly with each other. But it will have to be extra, outside the standard.
Can you go to the decision of why you use attributes instead of context-sensitive keywords?
The question was, why are we using attributes here? And the answer is to try to improve this transition story. And unfortunately, GCC right now, if you put in these attributes, even without the colon notation, it will look in the parentheses and try to parse it as an expression and do name lookup and everything in there, and report an actual hard error if it doesn't like what it sees. And so those things are going to happen to GCC, at least. Clang is a little better at ignoring what it doesn't like, but so far it only has something, a flag saying either warn about annotations or don't warn about annotations. It doesn't know, and we need finer control on that. But getting something that's not attribute, like retrofitted into existing compilers, sounds like a real uphill battle. Okay. All right, I guess that's it. Thank you for coming.